So we have talked about orthogonality in function spaces. Let's look a little bit more in depth about how this comes to be. If H is a self-adjoint operator, and we have two different eigenvalues associated with two different eigenfunctions, then the inner product between the two eigenfunctions is equal to 0, where the inner product is defined based on the Sturm-Liouville problem. Let's look at a proof for this. We will follow the steps that we used to prove the same theorem when we were looking at symmetric matrices. So let's review the steps we did for the symmetric matrices and see how this can translate to the setting of self-adjoint operators. For matrices, we looked at the applications of the matrix to an eigenvector, and we have the associated eigenvalue times the eigenvector. We do it twice, so for Vi and Vj. Then we use the inner product to multiply Vi times Avj and Vj times Avi. Then we have the eigenvalues that pop out of the inner products, and we are left with in the inner product of Vi times Vj and Vj times Vi. Because inner product doesn't change if you swap the order, and A is a symmetric matrix, then the first column is the same. So when we take the difference, they disappear. And the second column will have just lambda j minus lambda I times Vi times Vj. This allows us to say that Vi and inner product Vj is equal to 0. Let's try to bring this in the context of self-adjoint operators. So we have two eigenvalues and eigenfunctions, and we know the equation they satisfy. We utilize the inner product to multiply Yj with the first equation and Yi with the second equation. The eigenvalues pop out of the inner product. H is self-adjoint, so we know that Yj times Ayi is equal to Yi times Ayj. So when we take the difference, the two left-hand side cancel each other out, and we are left with lambda I minus lambda j times the inner product of Yi times Yj. Therefore, the inner product of Yi times Yj needs to be equal to 0. So you see, formally, we have done exactly the same steps on the two sides. On one hand, we use the property of the symmetric matrices. On the other hand, the property of the self-adjoint operators. But we have taken formally the same steps. What you have to remember is that in one case, we have looked at vectors, and the other case, we have looked at functions. So let's try to use this and take advantage of the strength of this statement. Let's look at the projections out of an orthonormal basis when we're looking in the Rn. So if in Rn we have V1 to Vn, an orthonormal basis, for any x vector in Rn, we can write the vector equal the orthonormal basis we just used times some coefficient. And it follows from this that the coefficient needs to be defined as the inner product of x times Vi. So why does it follow? Well, because if we multiply our split, so our x and our sum of xi Vi by one of our eigenvectors, so one of the elements of our orthonormal basis, let's take Vi, then in the sum, the sum of going from I to n of xi Vi, inner product with Vi, well, all the elements except the one associated with Vi times itself disappear away because of orthonormality and the linearity of inner products. So we're left with the equation that xi is indeed equal to the inner product of x times vi. Does it translate to functions? Can we use the eigenfunctions of a self-adjoint operator to span a function space instead of a vector space? Yes. Actually, it works exactly in the same way. You only have to think of functions in the same way as you think about vectors. And I'll try to explain how this works. Let's go back to our previous example. So we have our self-adjoint operator that takes y and returns as minus y second. We have some boundary conditions. So we introduce the space of functions. We call it L2. And you'll never have to care why we called it L2. And this is a space of continuous functions from 0 to L, where v0 is equal to vl is equal to 0. Any function that belongs to this space can be written as a sum, infinite sum, of some vi times yi, where yi is the ith eigenfunction associated with the self-adjoint operator h, provided that we rescale it in such a way that yi times yi is equal to 1 for all I. On top of this, on top of the fact that we can do it, we also know that the coefficient that we need to use is the inner product of the function with v that we're looking at times the inner product, the eigenfunction we're looking at. And we're following the same steps that we used for the Rn case. Well, the form is the same. In Rn, we're talking about a finite sum of elements, while in L2, we're talking about an integral. When we're using inner products, in Rn, we are matching elements in a vector and summing all of those products up. In L2, we're taking an integral with a weight. So formally, when you're taking the integral of an infinite sum of a function, you can swap the integral and the infinite sum only if both the sum and the integral are bounded, so they're not infinity. We are assuming this to be the case. The take-home message is that function spaces can be treated as infinite dimensional vector spaces. What we haven't proven, and I don't plan on proving it, is that indeed yi for I in n is enough to cover all the function space. I also haven't really talked about what sort of function space we actually need for that to work, but neither of the two topics is going to be covered.